Hi guys, this is going to be a video lecture of sound waves. Alright, what's sound waves? It's basically a vibration of the air molecules. And this is a tuning fork, and when you actually hit it, then you're going to see that, well, you're not going to be able to see, but if you can actually look at it, it's going to move back and forth. And when it moves back and forth, then air molecules are going to basically compress and then rarefact. Compress, rarefact, and that's how you basically transfer the energy through the air molecules when you create a sound. And since the vibration and the direction of movement of a wave is perpendicular, then that's becoming a longitudinal wave. And what's audible sound wave? It's basically we are not able to hear everything, all of the frequencies. We have certain range actually that we can hear, and that's roughly 20 to 20,000 hertz. And of course, this is not like exact for everybody, but that's an average thing. And every animal has their own audible sound range. So elephants, for example, are going to be able to hear low frequency sounds because of their large ears. And dogs, we have dog whistle, for example, and when we actually blow it, we don't really get bothered by that, but dogs are getting crazy because they are able to, those dog whistles are creating a sound wave that is more than 20,000 hertz, so it doesn't really bother us, but it's basically within their audible sound waves, so they basically get bothered by that. And dolphins, they also have really high frequency range that they can hear. And we also have certain, like the wave ranges or frequency that is above and below that audible sound waves are going to have special names. Infra means below, and ultra means beyond. So anything that is below 20 hertz, then it's going to be infrasound. Anything is above 20,000, which is the upmost highest frequency that we can hear, is going to be our 20,000 hertz. Anything beyond that is going to be ultrasound. And speed of sound. So speed of sound is actually going to change because remember, speech depends on medium. So when medium changes, then speed of sound will change. So medium in that case will depend on, of course, the material. So liquid, solids, and gases. And if you would like to check this out, then you will see that speed of sound in air or in gas is roughly almost all of them except hydrogen in 0 degrees Celsius are always less than what they have in liquids, and they're always less than what they have in solids. And again, that's a general thing. You can't really say all gases are going to travel slower. But the idea behind this, it's basically how quickly you transfer the energy from one particle to another. And once you think about those different phases, gas, liquids, and solids, in gas, air molecules are really far away from one another. In liquids, they are a little bit closer to one another, but in solids, they are basically right next to each other. So which means transfer of energy in those gases is going to take longer time, but in solids it's going to be a lot faster. So that's why speed in solids are going to be higher than what they are in gases. But again, that's just a generalization. There are some certain cases that is not applying to that rule. But temperature is also changing the medium, because remember, medium is basically what energy is transferring through. So in high temperature, low temperature, basically air molecules are going to be separated differently. So in that case, temperature will also change the medium. So in that case, we are going to have a new equation for speed of sound in air. So what does that mean? So V0 and T0 are your reference temperatures. So they're going to say at let's say room temperature, the speed of sound is something. Then let's say at 0 degrees Celsius, what is the velocity? All right, and one thing to be careful about this, Kelvin is your scale, so whatever you're using, you need to use temperature in Kelvin scale. Alright, sound intensity. So intensity of sound is basically how much energy is transferred per unit area. Alright, so let's say you're going to create some sound. So the energy of sound is going to travel, but as it travels, as you can see, it is traveling in a larger and larger distances and larger area. So that means amount of sound or amount of energy per area is getting less and less because you basically distribute the energy that you have to a larger scale, to a larger area. So in that case, an area is a two-dimensional thing, so it's basically changing the dimension into two axes, x and y. So that means the area is basically changing with r squared. And intensity is basically given by I. And as you go farther and farther away, so as r increases, your intensity is getting less, and your area is increasing with the square portion. So that means intensity will decrease by the square of the distance. And what is the unit for sound intensity? It's basically energy per area. And watts, it's basically power of, like power unit that we didn't see yet, but it's a power unit. So power per area. And the minimum sound that we can hear is basically threshold of hearing, and it is basically given by I0, and it seems pretty small number. It's 10 to the power of negative 12 watts per meter square, but the maximum, or not the maximum, but the threshold of pain is basically 1 watts per meter square. So this is actually a really, really huge number in terms of like the power of it is too high. But in numbers, it seems it's just 1. But again, in reality, that's a really powerful intensity. And sound level is another way to describe intensity, actually. And it is shown by beta. And it is basically sound level. One of them is sound intensity. It's shown by I. But I is changing with a different scale. So if you would like to double your intensity, for example, you don't just multiply this intensity by 2. You basically increase the power of it because the way that they have scaled it is a little bit different. So it's a logarithmic scale. So they decided to have another measurement unit for that. So it's a sound level thing. And the unit for that is decibels. And a way for us to calculate the sound level is as follows: 10 times logarithm of I over threshold of hearing, which is I0. So that means if you would like to decide, if you would like to calculate the sound level, you basically use this equation to describe the sound level in that region. So again, I0 is the intensity of the chosen reference level, and the logarithm is based 10. So we don't really see that 10 over here, but remember, logarithms need to have a number underneath. So for this, if there's nothing, then that means it's 10. And it is, so your I0 is basically your reference over here, and it doesn't have to be I0 all the time. It's basically your reference intensity, but most of the time it's basically taken as I0. And this is important. Every 10 decibel increases intensity by 10 times. All right, what does that mean? For example, if you have 0 decibel, what does that mean? It is the lowest intensity that we can hear. But if you would like to have 10 decibel of sound level, then if you look at those numbers, it is 10 to the power negative 12, this is 10 to the power negative 11. So what is happening? This is increasing by 10 and this is increasing by 10 times. Alright, let's see the whisper. So whisper is 30 decibels. So it is basically 10 and 30 times more, or 30 more. But if you look at the powers, then you will see that the power is changing by 3 times. So the difference in between 0 decibel and 30 decibel is actually 1,000 times more intensity. Alright, so every 10 decibel is increasing the intensity by 10 times. Alright, so if you basically go from 0 to 140 decibels, then you are changing the intensity by 10 to the power of 14. Alright, this is a huge amount of energy. Alright, so that's why instead of using this scale, they decided to use decibel scale, but decibel scale is measured a little bit differently. Alright, so this is how you measure the sound intensity, the decibel of it, but what is the relationship in between the intensity and the decibel? So if you would like to measure the intensity of it, let's say you know the sound level, but you're trying to figure out the intensity of it, then what you need to do is you basically need to solve this equation. You need to solve this equation for I. So to be able to do this, you basically need to get rid of this 10 first. So you divide both sides by 10 first. Then you have logarithm of I over I0. After that, you need to get rid of this logarithm. So inverse function of logarithm is basically taking the base as power. So once you take the base as power, then you basically get rid of this logarithm. So you have I over I0, but over here you're going to have 10 as a base and beta over 10 as power. Alright, so that's how you get rid of the logarithm. And after this, what are you going to do? You are basically going to cross multiply both sides. So your I is going to I0 times 10 to the power of beta over 10. Alright, so that's how you move from sound level to sound intensity. This is the relationship in between them. Alright, pitch of a sound, it's basically perceived highness or lowness of the sound, and it depends on the frequency. So high frequency means high pitch, low frequency means low pitch, and women in general have high pitch and men in general have low pitch. So frequency for women is higher and frequency for men is, in most of the cases, lower. And high frequency is called shrill sound and low frequency is called grave sound. Alright, standing waves. Standing waves is not just about sound waves, it's basically any waves. In this case, you are seeing that on a string. So it is the result of interference in between two waves traveling in opposite directions. So what is happening over here? So you basically create a vibration over here. And this is the vibration, and it is basically traveling along the string, but whenever it hits to the end, what is happening? It is basically reflecting. But when it reflects, it's basically reflecting by flipping. So basically, as a result of this flip, there is a continuous, or there is a certain shape that you can create. At certain frequencies and wavelengths, you are going to be able to create this shape. and it's going to seem like it is basically standing there. It's not moving. However, this is a continuous movement, but at certain frequencies and certain wavelengths, at some point, all of the moving forward waves and coming, like returning waves, are going to interfere at the same location with the same amplitudes all the time. So, for example, at this point, at all times, all of the going waves and returning waves are going to interfere at this location, at that specific location, as like this. So they are going to cancel each other out at this location at all times. So then you're going to see this point not moving, and we call this point node. And at this point, you're going to see two waves, the going wave and the returning wave. They're always going to interfere constructively, and it's going to basically create the maximum amplitude it can get, and we call it antinode. So basically, this is the result of interference, and there's a continuous interference on this string throughout, and basically as a result we get this shape, and this shape is known as standing wave. And node is the stationary point, antinode is the where you have maximum amplitude, and it is basically halfway in between two nodes. And another very important thing, so we can, by looking at the standing waves, we can actually measure the wavelength of the standing waves. So how does that work? So for example, one wave, one complete wave is going to move as follows. All right, this is one repeating pattern of a wave. So in this case, what do we have in here? Let's say I know the length of this distance. Then I can say the wavelength of this guy is equal to L, right? Because this is the repeating pattern. So this shape is the repeating pattern, and it is basically one complete wave, and it is basically repeating itself within that distance. So I can say this L is equal to my wavelength. But this is actually not the simplest one. The simplest wave that you can actually have is this shape. And what can we say about the wavelength of this shape? So if we think about it, this part is not actually the entire wave yet, because entire wave requires us to go up and down, but here we only have the up part. So if this distance is L, then I can say my half wavelength, because this is not the complete wave yet. This is my half of the wave. I also need another half. So the entire length of the wave is going to be basically 2L. Alright, so considering that, we are basically saying that one loop, those shapes are called loops. So one loop, this is going to be the rule, is always equal to half of the wavelength. So if you have two loops, this is basically one full wavelength. So if you have three loops, you have half of the wavelength. Alright, so this is very important for standing waves to make calculations, because this form is not going to be the only case. We are going to have standing waves in 3 different cases. And let's see what they are. So we basically have 3 different scenarios. So those scenarios are depending on the case. So you are going to have cases where we have one end open, one end closed systems. So you're going to have cases where you have 2 ends closed, and then you will have cases where both ends are open cases. So for those three different systems, we are going to have different standing waves. And we have one definition: the lowest frequency of a vibration of standing wave is basically fundamental frequency. So to be able to create this pattern, for example, this wave pattern, you're going to require the lowest frequency that you can ever have, and this is your fundamental frequency, and it is shown by F0. So to be able to create this shape for both and closed systems, you are also going to need a frequency, and this is also your fundamental frequency. And these shapes are the simplest waves that you can actually fit into those three different cases. So the lowest frequency that you have to create the simplest wave in those three different patterns or three different systems is called fundamental frequency. And the shape of the wave will change from system to system. So as you can see here, you have quarter of a wavelength, half of a wavelength. This is also half of a wavelength. We're going to see them in a minute. All right, so what is harmonics? So for those systems, we basically use the term harmonics. It is the simplest vibration that can occur on a wave. Is called harmonics or first harmonic or fundamental frequency. So for example, to be able to create this pattern, this shape is your first harmonics, and the frequency that you need to create this shape is called fundamental frequency. If you are talking about two-end open system, then this is your simplest wave that you can fit in, and this is your first harmonics, and frequency that you create this shape is called fundamental frequency. And if you're talking about one end open, one end closed systems, the simplest wave that we can fit in is this shape. And this is my first harmonic, and the frequency that I create this shape is called fundamental frequency. So to be able to create those patterns, actually, there are different methods to create it, but the simplest way, I believe, is adding a loop to move to the next harmonics. What do I mean? This is one loop. So if you would like to get the second harmonics, you basically add another loop. So in this case, this is two loops, second harmonics. If you would like to get the third harmonics, you basically get another loop added to the system. So this is third harmonics. So for all of them, this is going to be the case. So this is, let's see how much wavelength we have in here. So here we kind of sort of described in the previous one, but this is one loop. So this is half of a wavelength. So what do we have in here? So this section is not half of it, but it is actually half of the half. So we basically get this section in here. So this is quarter of a wavelength. But I don't have just one quarter, I have another quarter over here. So I have two quarters. So here I have, again, half of a wavelength. So this is also half of a wavelength. So this is one half, second half, this is one full wavelength. This is 1, 2, 3 halves, so it's basically 3.5 wavelength. So to be able to get the second harmonic for the next system, you again add a loop. To be able to get the third, you add another loop. So, but the rule says at open ends, you cannot have a node. You need to have an antinode. So your ends are always going to have this shape, but in between you can actually add loops. So what do I have in here? So ends are one half, you added another half, so this is also one full wavelength. So half, another half, this is 1. Adding of those 2 quarters is going to make another half. So I also have 3.5 wavelength in here. So both end closed and both ends open systems are pretty similar systems. The only difference is the shape. But if you are talking about one end open systems, the first harmonics is not going to be half of a wavelength, but you are actually going to have half of the half, which is quarter of a wavelength. So you are going to need, the smallest wavelength that you can have is quarter of a wavelength. The simplest wave that you can fit in. So if you would like to if you would like to move to the next harmonics, you are going to actually need to add another loop again. So the rule is not changing. The name, however, will be third harmonics. So that was first, and this is third. So in the previous ones, it was first, second, and third. First, second, and third. But here, next one will be third. And in a minute, I will explain why it becomes the third harmonic, but not the second. So how many wavelengths do I have in this system? I basically have a quarter here, and I have a half in here. So basically, my wavelength in the system is 3/4 of a wavelength. And what do I have in the last one? Half, another half, a quarter. So basically you have 1, 2, 3, 4, and 5 quarters. So this one is going to be 5/4 of a wavelength. Alright, so these are basically how we calculate the wavelengths that we fit in those 3 different systems. Alright, so if we want to dig in more then and actually do some calculations, the first harmonics is again the simplest way that you can fit in. So within the length L, what do I have? This is basically one loop. And remember, one loop is equal to half of the wavelength. So what does that mean? This length L, let's say this is 2 meters. Alright, this length is 2 meters. Then what does that mean? Half of my wavelength is equal to 2 meters. Then what is the wavelength of the wave? It is 4 meters, or it is 2 times L. Alright? And the frequency that I need for this guy is called the fundamental frequency. Then if you want to move from velocity equation, velocity equals frequency times wavelength. So since velocity depends on the medium and we are using the same string all the time, my velocity is going to be the same at all times. So what does that mean? The first frequency times first wavelength is going to stay constant throughout. Alright, so let's leave it over here and then we're going to revisit this guy. So my F1 is also my fundamental frequency, and most of the time it's also shown by F0. Alright, so if you move to the next case, it is my second harmonic this time. So this time I have 1 and 2 loops. So what does that mean? This entire length L, which was 2 meters that I decided, this is going to have one wavelength, half, another half. In total, it's going to have the entire wavelength of the wave. So what does that mean? My wavelength is actually equal to 2 meters. or my wavelength for the second scenario is actually directly equal to the length L. Alright, now let's revisit this equation. So now I have second frequency that I can generate this. And the first one, lambda 1, is actually equal to 2L. And lambda 2, the second wavelength that I'm going to need for this, is just L. And let's visit this equation one more time. This is constant, we said. Then what does that mean? F1 times lambda 1 is equal to F2 times lambda 2. So F1 is my fundamental frequency, F0. Lambda 1 is 2L. Then what is F2 going to be in this case? Lambda 2 in terms of L is just L. So L's will cancel out. Then what do we have in this equation? We are seeing that F2 is actually equal to 2F0. Alright? So that's what we have in here. So if you want to continue with the third one, then what are we going to have for this case? So now I have 3/2 of a wavelength. So what does that mean? 3/2 of the wavelength is equal to L. Then what is my lambda 3 then? Lambda 3 in this case, 2L divided by 3. So my lambda 3 is actually equal to 2L divided by 3. And my frequency for this system is going to be F3. And let's again revisit this equation. F3 times lambda 3 is a constant number, which is F1 times lambda 1. Then your F1 is F0. And your lambda 1 is equal to 2L. And your lambda 3 is 2L over 3 and F3. So if you do the math, L's will cancel out again, 2's will cancel out. Then what are we going to have? F3 will be equal to 3F0. And as you can see, if you continue doing this more and more, you will see that the fourth harmonic will become 4F0, fifth harmonic will become 5F0. So that means the nth harmonic is going to have F0 times F0 times the n. And your wavelength is always going to be 2L divided by that n, and n is the number of harmonics. And this is a system for both enclosed systems. Alright, so this is going to be very similar and actually exact same thing. The only difference that we have over here is the shape. Because this is also half of a wavelength, this is a full wavelength, this is 3.5 wavelength. So if you do the same math the way that we did in the previous one and consider F1 times wavelength 1 is equal to V, and it is a constant number, then you are going to be able to set this up as F2 times lambda 2 equals F3 times lambda 3, and that goes on like that, and this is equal to F0 times lambda 1. So, and all of the lambdas can be written in terms of L, and once you do that, follow the same procedure that we had in the previous part, you will also see that the second harmonic is going to require 2 times of the fundamental frequency. If you're looking for the third, it is going to require 3 times of the fundamental frequency. Alright, so if we have both ends open system, then your fundamental frequency is again the multiple integer multiples are going to be the frequencies for the second, third, fourth, fifth harmonics, and it's going to go on like this. But if we have one end open systems, so in the previous one we were going with half of a lambda, but this time we're going to go with quarters of lambdas. So the first one is going to be quarter of a lambda, and the second one is 3/4, and the third one is going to be the 5/4 of a wavelength. So in that case, once you do the math, f1 times lambda 1 equals f2 times lambda 2. But in this case, f1 f1 is going to be f0 times lambda. My first lambda is equal to, my first L is equal to quarter of a wavelength. What does that mean? My wavelength is equal to 4L. So my lambda 1 is going to be 4L. Then what do I need to do? I need to move on to the next frequency, which is f2, and see what's the relationship in between f0 and f2. So my lambda 2 length, the same length, is equal to 3/4 of a wavelength. So what is the wavelength in terms of L? 4 goes right there. 4L divided by 3. So my lambda 2 is actually 4L divided by 3. So if you want to rewrite this entire equation here a little bit better, 4 f0 times 4L is equal to f2 times 4L divided by 3. So in this case, 4L's will cancel out, and this guy is going to go up here. So my f2 will become 3f0, not 2f0. And if you continue doing this, then you will see your wavelength over here. You have 5/4, so 5/4 of a wavelength is equal to L. Then your wavelength, your lambda 3, is equal to actually 4L divided by 5. So in this case, the only thing that is going to change in here is this 3, and it will become 5. So what does that mean? Your f3 will become 5f0. So that's why for this next harmonics, you're not going to become second, but you're going to get third harmonic because it is 3 times the fundamental frequency. And the following one is going to be fifth harmonic because it is 5 times the fundamental frequency. And this is going to basically go increase with the odd integers. So if you're basically going for nth harmonic and frequency of that nth harmonic, then it is going to be basically 2n minus 1. This is basically the equation for odd number in math. So you just basically plug in the number, and then that's going to be the equation for you. And this equation is basically going to be the wavelength of nth harmonic. Actually, it's not nth harmonic. Nth resonance, that's what we actually call it. The resonance, basically when you create those standing waves. So when you are creating those standing waves, you basically create, or you resonate at those frequencies. So the third time that you resonate, this is your fifth harmonics. The fourth time that you resonate, this is your seventh harmonics, and it's going to go on like that. All right, Doppler effect is the next thing. It is basically the relative motion in between two things, and one of them is the source of the frequency, the sound. The other is observer. So if there's a relative motion in between those two objects, then you are going to have the Doppler effect. So in Big Bangs, actually, there was one episode that they were talking about this. So basically, when an object is getting closer and closer to you, it is going to send, the regular sound wave is basically increasing like this. It's basically creating the same wavelength in every part. And it's basically 3D, so it's going to create the same wavelength throughout. However, if the sound source is actually moving, or if there's a relative motion, then it's going to seem like this. You are going to create the sound waves, but you are also traveling in that same direction. So what does that mean? So the wave in front of you is going to get closer and closer to each other, but the wave in the behind is going to get farther away from one another. So what does that mean? The wavelength in the back is more, the wavelength in the front is less. So, and again, considering this frequency and wavelength relationship and the velocity of sound, and velocity of sound is basically depending on the medium. And medium is not changing, so my velocity is not going to change. However, wavelengths are changing. So how is it possible? So if wavelength is less, then your frequency is going to be high. If your wavelength is more, then your frequency will be less. So that's why if something is getting closer and closer to you, if a sound source, then you're going to start to hear with higher and a higher pitch. And that's because it's going to have higher and higher frequency. And as it passes by, and then as it moves on, the sound is going to die out. And that's because the frequency is getting less and less. And of course, the intensity is getting less and less. But wavelength is more, so frequency is less. And that effect is basically known as Doppler effect. And this is the end of the presentation. I know this is a long presentation, but this is going to be basically the core of your chapter test about waves. You're going to have a couple of questions about this particular presentation. So I also advise you guys to watch the question solutions, and that's basically how they're going to complete this lecture, because this lecture alone probably is not going to make too much sense. Alright guys, see you in the next video.